In the third part of the RayTK optimization series, we'll cover some aspects of how RayTK works under the hood and talk about ways that we can change parameters to improve performance. I highly recommend watching the first few videos in the intro series before this one, at least up through the SDF section, since we're going to be talking about how the toolkit works. As with the previous two optimization videos, the goal here is to reduce the amount and complexity of work that the renderer is doing. We're focusing here on the parts of a RayTK scene that are contributing code to the renderer. So basically, any operators wired into the inputs of the renderer, all the way up that kind of tree. But that doesn't include stuff like, chops or other operators that are animating parameters or something, or any of the post-processing stuff like a render select. So we're just talking about the things that are directly wired into the renderer. As we covered in the intro series and the first video in the optimization series, basically all of RayTK's work is done within the renderer, within a single shader in a GLSL multitop. In some ways, this is kind of counter to how Touch Designer generally behaves, where work is often spread across many operators that are applied in some sort of sequence. So in order to do everything needed to render a scene, that shader has to do a lot of stuff. And that means that there is going to be a lot of shader code. So just looking at the code for this relatively simple scene, we've got more and more and more, and so much of it continuing all of that. So 2,743 lines. Not all of that is running all the time, but it's still a lot for the GPU to handle. So in order to actually use that shader, the GPU has to first compile that text, that shader text, into first a standard bytecode format, which is kind of like sort of machine code, but more standardized, and then eventually it compiles it into, the specific stuff that your exact GPU model handles. And once that's all done, Touch Designer can run the shader and then get the resulting images out of it. For the kinds of shaders that you typically see in Touch Designer, that whole process is pretty transparent since the shaders are relatively simple. But things are different when the shaders are as huge as they are for RayTK. So the process of compiling the shader can take multiple seconds or even a minute in particularly extreme cases. And the way that Touch Designer is implemented, the entire process stalls while that happens. So just to demonstrate that, you get that little stall when something is connected or disconnected. And the impact of that increases when there's more complexity in your scene. So for something like this, it's not too bad, but it can become a problem. Perhaps at some point in the future, that will be implemented asynchronously, so you'd be able to continue using the rest of Touch Designer while it's doing that, but I don't think that native support for that within Touch Designer itself is likely to happen soon. So the result is that we get those stalls. To avoid having that stall happen, RayTK tries to avoid changing the code whenever possible. But there's a trade-off between that and how fast it runs. So what kinds of things cause the code to change? The first time that any operator is connected or disconnected in a network, it's going to have to recompile. And so you can see the little dip there. It's going back. And at least the way that things are currently implemented, if you undo something and you go back to exactly what it was previously, it still has to recompile. It doesn't kind of save previous compiles, at least not for this kind of change. Oh, another kind of thing that can cause that recompile is when the type of value that an operator is producing changes, or the type of coordinates that it's using, or something like that. So we've got a band field down here. Now this band field can either produce a single number, or it can produce a vector which can be interpreted as color. So it has a return type parameter here, currently set to float. So we're only, the render 2D is, just showing that as transparent to white. But if we change the type there, then we get, colors showing up in there. So that means that how the render 2D is going to interpret what's coming out of this field is going to have to change, which just means the code's going to have to change. There are also some other kinds of parameters that will cause a recompile, which we'll discuss in a minute. That brings us to parameters. So we're going to talk a little bit about how parameters get passed into shaders. So the details of the code here aren't important, just the general concept of how the parameters are working is what we're focusing on. So there are a few different ways that parameters get into a shader. First, there are uniforms, which you can set on this vectors page. You give it a name, you put some numbers in there, maybe they're expressions or something, and that gets kind of pulled in. And those values can change easily, and there's very little cost in getting those new values into the shader. The downside of that is that the GPU can't really make any assumptions about what those values are going to be, and that means there are some kinds of optimizations that it can't do. Next, there are just inline constant variables or macros, where it's just directly in the text of the shader. This allows the GPU to make all kinds of assumptions about what this value is going to be. It knows it's always going to be 12 in this case. So, if there was a piece of code that was checking, if it's equal to 7, do whatever, it knows that it's never going to have to do that, and so it can kind of strip out parts of the code. So the benefit of those is that they can, be optimized really well. The downside is that it requires changing the code of the shader itself in order to put a new value in there. Then there are called specialization constants, which are kind of a halfway between those two approaches. How they work is when the GPU is kind of doing its first pass at compiling it, it will leave a kind of placeholder in the code. And then when it does the second phase of the compiling, it inserts whatever that value is. So it does kind of a lot of the work of compiling beforehand, and then when you give it an actual value, it kind of can finish the job. The huge benefit of these is that when that value changes, it caches the code that it compiled already. So let's say, if this were to start at a value of 1 and you change it to 2, okay, it's going to have to recompile. But if you go back to 1, it already knows how to do that, so it doesn't have to recompile. And you go back to 2, same thing. Then if you go to a different value, like 4, it's going to recompile and so on. So it will keep some number of the last few values that it's seen for that and kind of cache those and be able to switch between them cheaply. So how does all of that factor into RayTK? In RayTK, parameters start as custom parameters on different operators in your network, and then they get pulled into the shader in the renderer in different ways. There are runtime parameters, there are baked parameters, and then there are semi-baked parameters. To figure out which of those categories a given parameter is in, we can look at the documentation. And to do that, we can use this little help button on that operator. So that will show us a table of all the parameters. And then we've got this column here for regular handling. So these first three are runtime parameters. And then this UV mode is semi-baked. We're going to talk about this read-only column later on. There are some operators where that isn't documented, but in general, most parameters should have it. The most common type of parameters are runtime parameters. These are things like the thickness on this SDF, and they can change as much as they want with kind of negligible impact on performance. And these are using shader uniforms. And it's true for lots of different things. So, vectors with multiple parts, individual numbers, and so on. Next are parameters that, in order to run efficiently, are always baked into the code. So anytime one of these parameters changes, it causes a recompile. An example of this on segmented line SDF, just switching over to that, is the number of segments. So anytime that we change that, we're going to get a full recompile install. And that's because the way that this operator is implemented, it's important for the compiler to know ahead of time how many segments there are going to be. Some menu parameters are also treated like this. For example, in the cone SDF, the mode here will cause a recompile. And it's because it's changing the approach that it uses, it's changing which parameters it's using. And so in order to handle that efficiently, it kind of bakes it into the code. Other menu parameters, like the axis on a revolve, switching over to that, are implemented with specialization constants. I'm calling these semi-baked since they're kind of halfway between runtime and baked. The first time that a semi-baked parameter changes, so we're currently on X, going to go to Y, you get that compile rate drop. But if we then go back to what we've been previously using, it can switch between those without any recompiling. Next, we'll talk about a way to take parameters that would normally be runtime and tell RayTK to bake them in directly. We're going to do that by marking the parameters as read-only. We'll be looking at this large scene here, which has a couple SDFs and a bunch of fields controlling stuff, 2 different modular materials, and so on. So a lot of stuff going on here, 185 parameters, lots of code. And if we switch it on, the performance is terrible. So bad that it actually interferes with the recording of this video, so I'm gonna switch it off for now. One important way to think about the scene is about which parts are changing and which parts are staying the same. So right now we've got a couple different speed generators, LFO generator, that are changing a couple of parameters. We've got, rotate XYZ there, we've got phase here. So we've got a few of them in the scene, but everything else is staying the same. So using this read-only trick, we can tell RayTK that it can assume that those are always going to stay what they are, and that allows it to optimize things a lot more. So for comparison, I've made a version of this scene that uses this optimization technique heavily. So that, and we're still getting 60 frames a second, and the output's basically the same. Except for the color, because I used the wrong setting. So let's step through some examples of how we get to that point. So I have another copy of it in here. Let's just go in there and take a look. And I'm actually going to switch the renderer off here because, again, this one is so bad that it interferes with the recording. Some of the highest impact places where you can use this read-only trick are on menu parameters. Now, not all menu parameters support this, but in general, it shouldn't hurt. And if you do encounter issues where making a parameter read-only causes an error or something changes in the render output, let me know, and you can report that as a bug, and I'll fix it. And I've got a link in the video description about how to report bugs. But in general, making things read-only should either be harmless or helpful. So let's go over to this method here. So let's see what happens when we change the method there. So performance is still terrible, but we aren't seeing a drop for a recompile. And that means in order to be able to do that, the shader has to include all the different code for all the different possible options here. Then it passes in a number parameter, and anytime that it's doing shading, it checks that parameter and goes to the relevant chunk of code. But since we aren't going to be changing that, we can bake it into the shader. So let's do that. Right-click on the parameter and then choose Toggle Read Only. We're going to get a stall while it recompiles, and it's a long stall because of the complexity of the scene. But fortunately, that will improve as we do more of these optimizations. So now the shader is only including the code for that one specific method that we have selected. Now, as you may have noticed there, performance is still pretty bad. And that's because each of the parameters that we're optimizing here will generally have some impact, not a ton. But if we can apply it in lots of places, it adds up to a reasonable amount of improvement. So let's now apply the same thing to a few other operators. And a useful trick when you're doing this to multiple operators with a parameter with the same name is to select all of them in the network editor and then do it there. And in theory, that should apply to all of those operators. And since that's only kind of all happening at once, you only get one recompile instead of having to do it for every one, interchanging one after another. There are occasionally bugs in the network editor that will make it not do that. So I guess that's what's happened here. So we might need to actually just go through them one by one. So now let's take a look at the performance, and it's still pretty bad. Maybe slightly improved, but definitely more work to do. So we still are kind of in that problem range, maybe slightly improved, but there is more to do. Let's take a look at a noise field. So just going to switch things back on and then try changing the noise type to read only. So when we do that with the noise type here, we don't see any change there. So that means that this noise type is already being baked in. And in this case, it's doing that because the amount of code needed to support all the different types of noise would get really excessive, so it kind of always makes you bake it in. Now let's try it with the axis parameter. And with that one, we do get a recompile. That means that it is now changing it to be baked in. Now, there is also a coordinate type parameter in there, but that's not going to be changing anything if you make it read-only, since changes to types of values that are passed around always have to be baked in, and that includes pretty much anything named coordinate type or context type or return type. So now let's try that. Starting to maybe look slightly improved. Maybe slightly improved. But we can also do the same thing over on Helix SDF. So again, we have an axis. Let's switch it on there. We can also do the same thing over on this wave field. Now, for me, at least, this one is a big help because I tend to use a lot of these. So just locking in that wave type. So I'm never going to change it from a sine wave to something else. I can have it just include that instead of all the different types. And then over on this polyhedron SDF, there is a combine mode thing for combining the different parts of that shape. So it can also be optimized like this. So now let's see what it's like with all of those. And that baseline is starting to be a little bit higher than it had been. Again, not much, but these things add up. So in general, what you want to look for are cases where an operator can do things in one of several different ways. And often that's controlled by a menu parameter, and locking those in with this read-only trick will simplify the amount of code that's going in and allow it to be optimized more effectively. Now, there is also one of these on linear clones. We have a combined type there, kind of similar to what we had on the polyhedron. But in this case, at least for this operator in this version of the toolkit, that one is always treated as semi-baked. So making it read-only wouldn't change anything. But I may change that in future versions just to have it be more consistent with the other operators. And we can also use this same type of approach for other types of parameters. We'll go over to our helix. So for the helix, we can also do it to this reverse toggle there. That's going to cause a recompile. And we can do it to numeric parameters, lots of different types. So I'm not going to do it just for saving time, but we could do it to translate here. We could do it to all of these since this never changes. And we can apply that throughout the network. And each one of those will give us a little bit of a boost. There are also some operators that have a built-in feature where there is a toggle called optimize. So range is a good example of that. Now, this feature, when we switch it on, it will look at the parameters and try to optimize as many of them as it can. So for any parameter that has just a constant value, it will basically bake that in. So it's the same as marking all of those as read-only. For parameters that have expressions in them, though, it doesn't. It keeps those as runtime parameters since it assumes that they might change. It also cuts down on the code, so individual operators will do that in different ways. Another example of this is the rotate operator. It has an optimize there, and it will generate different code that just includes the specific features that we're using. So even though it isn't able to optimize out this rotation amount, the order and all that other stuff, pivot, all that stuff is being baked into the code, into a pared down version of that code. Now let's take a look at performance now. And we're definitely getting a better baseline. So it was kind of further down near 20 frames. Now it's a little bit closer to 30. So again, this is a lot of little improvements. Now, just for comparison, the version where I've applied that to lots of stuff is running at 60 frames a second. So that's got, using a lot of these parameters marked as read-only, not all of them, but lots of parts here. And so just kind of consistently applying that approach to whatever operators you can will add up to a good improvement in performance. So that's it for this section. Thank you for watching, and make sure to like and subscribe.